Hey there everybody, this is LJ Wapker from P4.org. We held our first P4 user workshop at Stanford in June of 2015. We had about a dozen different demonstrations from multiple vendors and academics who were all working on various P4 targets and tool sets. We got a few of them recorded and are posting them here on the P4.org webpage for people to watch and hopefully get a better idea of what sorts of things the community is working on. I'll apologize in advance for some of the background noise and the not exactly Hollywood production quality. We were recording these live and trying not to get in the way of people who were there attending the workshop in person. This video is of Andreas Vollemy from Yale University, walks us through the Magellan project and how it works with P4.
Alright, so this project is Magellan, demonstrating Magellan. And Magellan is all about providing a very natural, familiar programming environment for developing forwarders. So, even with OpenFlow and P4 gives us a pretty nice programming environment, but it still has a lot of sort of odd aspects to it. So, for example, you can only use mention a table once in your control program. And on certain targets, you have a lot of target dependencies. On certain targets, you'll have things like certain operations that always execute out of order. No matter where you execute them in your pipeline, they'll be executed out of order. And that can cause all kinds of strange bugs if you're not aware of it. So in this project, we're basically trying to provide a programming model that's very familiar, sort of like this. It's kind of like JavaScript-y. So you would basically define your forwarding program as a function. And the idea is that this function is packet handling. It has a bunch of input variables that it works with. For example, the ingress port and Mac source, Mac dest. And then it does any kind of computation that it wants and has to set some distinguished output variables. And that's how it gets its job done. And this program can have things like lookups into, can have system state, for example, like hash tables or key value stores, like a Mac table. And you can do lookups, like, for example, to do lookup on dest, for example. And you can also have things like loops, so you could have a deny. We have procedures. Also, you don't have procedures in P4. Things like just normal software development tools, you don't have it in a language like P4. So here you could say, if deny, that's just a procedure call, then set the egress to be an empty list. And so this deny function is, it's declared separately, and you could have something like a loop in here.
Okay.
So pretty ordinary piece of code. And the challenge now is how do we map that down into, how do we execute that on P4? Because P4 doesn't have a lot of things. It doesn't have loops. It doesn't have things that can update tables. So in a sense, this is strictly more expressive than P4. This can do things that no P4 program can ever do right now, without amending P4 in a huge way. And so actually when we compile, when we want to run this, we need to, in general, generate two pieces. One is a data plane, and using P4, and then also a runtime. Basically something that's running on a general purpose CPU that can fill in some of the missing functionality. And so with P4, we need to figure out, to lay out this P4 data plane, we have a compiler that basically goes through a bunch of steps. It starts with a source program like this, parses it into an abstract syntax, and then compiles a kind of linear intermediate representation, which is a kind of assembly-like type of representation. And we do a lot of static analysis here to improve the code and to identify certain special operations that correspond very nicely to things that can be done with flow tables. So basically what we do is we have an instruction set that looks something like this, where we basically take an instruction, an intermediate representation for a general purpose language, and then add a couple new instructions. Like this one is an instruction that assigns to a variable based on some kind of packet access. And that packet access, you can have several different kinds, and one of them, for example, is a lookup. You look up into a table with some key expression, like, for example, look up into the Mac table based on the ETH dest. So that's a kind of, so it's So basically, as a result, what we get is an instruction set that's kind of general instruction set with a couple special instructions, domain-specific instructions added to it. And so these special instructions become the candidates for tables, flow tables. And to actually, another problem from going from this, something like this, even though we may have the intermediate representation, there's still a problem that the assembly code can have loops. And we can't, lay out a table and have it jump to itself or jump to a bunch of tables and come back to itself. So we need to unroll these loops. And we want to do this dynamically because we don't want to put a bound on the loops, the size of loops. So we do some analysis. The compiler actually does analysis where we take the control flow graph from the original program after getting the intermediate representation, and then we form the acyclic, strongly connected components from this control flow graph, and that'll give us an acyclic graph. And from this, we find a few instructions that we want to map into flow tables, and these become, then we get a table design out of that. And then from that table design, we can analyze the paths through this to actually find out what kind of actions, to get the actual actions that should happen from starting from each table. So I'll show you this in action. Basically, I have a demo that starts with the Magellan source code, produces IR, a table design, and then generates two things. One is the P4 data plane, and the other is a controller that cooperates with that P4 data plane. We use the software, the P4 software switch, to actually get an executable here, and we run that inside of Mininet, and then we just run the controller, and we can issue commands from like a northbound interface. So I can show you the process here. Let's see here. Okay, so I have a few source programs. We'll start with a kind of basic one. This is essentially learning switch. So what does a learning switch do? It first starts with updating the MAC table based on the source and the ingress port. Then it does a lookup into the MAC table and gets this value D, assigns that to a variable D. If D is null, that means the lookup didn't find anything. And so in that case, we forward to all ports. So ports is a built-in function, and we set the egress. By setting the egress variable, we set where the packet will go, and otherwise we forward directly to that packet. Okay, so now I can compile that. So first we start out with this empty directory here, and if I tell the compiler to go, we'll start to see, wait a second. We'll see a bunch of files generated here. And so the first step is to generate this assembly code here. Essentially, you see label 1, you jump to label 2. Label 2 does some kind of lookup on the MAC table based on the source and ingress port. And then it does a jump. You can't see that here, but it does a jump. And then eventually it gets a lookup here, label 9, MAC table, ftest. So this is a kind of intermediate representation we get. We produce these control flow graphs. So here's the control flow for this program. Basically start at the beginning, and then you've got two outcomes here, which based on the lookup and a couple different paths. From that, we form this acyclic graph. It turns out this one's already acyclic to begin with, so this is easy. And we see that these are the two tables we're going to lay out. Okay, now we get to the table design. So we have two tables and then a terminal node, which is not really a table. It's just two. These are the two tables. We have the different paths through the original control flow, and from that we can actually get the actions that should be on each, the parameterized actions.
So is the table graph here like hand-generated, or is it automatically generated?
No, this was generated by this program. Right?
Okay.
Yep.
But there's, in a complex program, there's multiple possibilities of that, right?
Oh yeah, so we can do, I can show you, for example, we can do a more interesting one. So this is IP forwarding, where we've got, like we're doing some stuff with VLANs, and we're deciding whether to route or switch. So we've got route and switch, and then there's a route function, and then there's this route lookup and the switching. So if we do that one, I think it's D4. So we'll get a very different, much longer assembly.
Yep.
And we'll get very different, let's see here, we get a much more complicated control flow graph, you can see here, right? A much more complicated control flow graph. And you have things like, loops, for example, right? Because if I have a route lookup that's like iterating for each route in the route table, look up and try to match, right? So you get these loops here. Then we form the acyclic graph, and this guy no longer has loops because we merge all the loops into a single node. And then here you see the top candidates for tables. So you end up with a much more complicated table graph. And you can see how many different paths there are. Each of these needs to have actions analyzed and produced for these different paths.
How did that loop look like in your high-level program?
So this one happened to be right here. So basically what this is saying is get the route table, get all the routes in the route table, and then just do a for loop over the routes. And check, the route, the IP dest.
So like, are you applying different masks? Or
yeah, so this is saying /24.
Okay.
Basically, the route table consists of a bunch of /24s, and we're saying just take the first 24 bits and compare it against that address in the IP dest. Yeah, so this is still, so now we're compiling this. This is compiling both the, it produces the P4 program, which is also, quite elaborate. You've got a lot of different actions here, and that you can get. You've got several tables, table 0, table 1, table 2, right? So table 1 happens to read on ether type because we're doing some kind of IP source learning. Here's Ethernet source, IP source, things like that. So that's the P4 program. So we can run this. What I can do over here is start up the so that's basically what I compiled here. I compiled a P4 program, compiled that P4 program into the software switch, and just started Mininet with that software, running that software switch as the Mininet. It's a switch in Mininet. Now I can come over here and I've got a controller that was generated for that one. I think this is so we get the controller up, and right, so initially you see the state, and okay, and I'm going to load up some rules. Basically, I've got a DB file over here, which just has a definition of like VLANs. So that IP router example, it assigns VLANs to ports and IP addresses to the gateway MACs. So it has these settings. So if we load that up, now we can see the state of the system. We've got all these tables populated. These are the kind of values for the system states. And then we can say show the rules. And there's a bunch of rules. So there's a whole bunch of, these are all the rules that we generated for that. So now we can do a ping all, and this is, the pings all go through. In the background there's some learning happening, and as associations are learned, both of IP addresses and MAC addresses to ports, we'll see the states are, there's more state built up, and the rules, a lot more rules have been populated. Right, so. And so basically it's been proactively populates all the rules based on what it learns. And so this entire controller is generated simply by starting with a source program, something like, in this case it was this source program, but it's just this program like this, and we automatically can generate the runtime rule population as well. So we really get both components.
Cool.